Let's take a look at a complete walkthrough of solutions to free response question number 5 on the 2025 AP Calculus AB exam. Now, this question is all about position velocity of particles moving along the x-axis. This is a classic problem type that comes up year after year, either on the free response or on the multiple choice. So this is a really great one for us to be practicing. Let's dive in. So, as I said, we've got two particles, particle H and particle J, traveling along the x-axis. We've been given some functions to work with. Let's see what we're being asked to work out. So in part A, we want to figure out the velocity of particle H. Well, what do we know about particle H? Well, we've been told the position. So the position function for particle H is e to the power of t squared minus 4t. All we have to remember here is that velocity is the derivative of position. So if I want to call it v sub h of t, that is going to be x prime, the derivative. And now I just need to apply the chain rule, right? Because this rule is, if I rewrite it, is e to the t squared minus 4t. So, crucially, I know it's a chain rule calculation because I have an inner function, t squared minus 4t, and I've got this sort of outer function here, e to the, okay? So to take this derivative, I need to take the derivative of the outer function. Okay, leave the inner function alone. So this will give me that same thing back because the derivative of our exponential function, e to the t, is just e to the t back. But I need to remember the chain rule. The price I have to pay is I multiply by the derivative of that inner function, t squared minus 4t. That derivative is 2t minus 4. So we have a rule for the velocity of particle h. Oh, but we didn't want the rule. We wanted to evaluate at t equals 1. So all we have to do here is say, oops, vh of 1 is going to be e to the 1 squared minus 4 times 1 all times 2 times 1 minus 4. Could just leave it like that and get full credit. We're not doing simple arithmetic. That's not how we're being graded on the AP, but since we're here, we may as well rewrite this as negative 2e to the negative 3. That is our final answer. So how are the points divvied up here? Well, I got 1 point for showing my work. Okay, I had to show something. So we had to indicate that we knew we were taking the derivative of that position function somehow. And then I get my second point for my correct answer here. Not too bad. Good job. In part B, we're asked to compare the particles. We want to know at what times between t equals 0 and t equals 5 are these particles traveling in different directions, okay, opposite directions. So we know that particle h has that position function, that exponential rule. For particle j, we're told its velocity is equal to this product of polynomials, 2t, t squared minus 1, all cubed. The crucial way into this problem is just to remember when I want to look at opposite directions, what tells me about the direction the particle is traveling in? It's the sign of the velocity. Okay. A positive velocity means we're traveling in the positive direction. Okay, positive. A negative velocity means we're traveling in the negative direction. Negative. Okay, so I'm just going to note here opposite direction. That means if and only if opposite signs for velocity. So we need to figure out what these particles have as their velocity, the signs of their velocity, and compare them. So from part A, hopefully you'll remember, we calculated the velocity function for particle h. So there, we calculated the rule was 2t minus 4 times e to the t squared minus 4t, just using that chain rule again. Now this looks a little bit complicated, but it's really not, because if we remember that this exponential function is always going to be positive for us. Okay, that is always going to take positive values. So the only part of this rule that can control the sign of the velocity is that 2t minus 4. So if we look at this 2t minus 4, that's a nice linear function. I understand when that is positive or negative. So in particular, at t equals 2, that velocity is going to be 0. And if t is larger than 2, I get a positive velocity. And if t is less than 2, I get a negative velocity. So that's us totally understanding the sign of the velocity of particle h. Let's now do that same analysis for particle j. So here we're told that v of j of t is 2t t squared minus 1 all cubed. But I'm going to set this up a little differently, and I'm going to factor that difference of two squares, t squared minus 1, as t minus 1 times t plus 1. And then I've got that cubed power that I'll just distribute to each of those factors. Now, while I've done this, this is going to let me set up a table of sine really nicely. Okay. Let me show you. Okay. So for this question, I'm only looking at t between 0 and 5. So my table of sine is going to start at 0. Okay. Now notice this velocity will be 0. Well, looking at this factor, we know it will be 0 when t is negative 1, but that's outside the domain that we're wanting to look at. It will also be 0 when t is equal to 1. That is in the domain that we want to look at, so let's add that to our table of values. And then I'll get all the way along to my t equals 5 setup. Okay, so let's see. What are my factors? Well, I've got a 2t factor, I've got a t minus 1 cubed factor, and a t plus 1 cubed factor. Okay. Let's see. Well, this 2t factor is going to be 0 when t is 0, but then it will always be positive for me. That t plus 1 cubed, well, starting at t equals 0, that will always be positive for me. So it's that middle factor t minus 1 all cubed that's really controlling what's going on here. So that will be 0 when t is equal to 1. If t is greater than 1, then I'll get positive values out. If t is less than 1, when I subtract that 1, I will get negative values. So I can now combine all this together to figure out that the sign of the velocity function is as follows. So I know I've got this 0 at t equals 1. Remember, for a table of sine like this, you just work your way down each of the columns and multiply the signs that you see. So I get a 0 at t equals 0. For that next column, I've got positive times negative times positive. That will give me a negative. Then got that 0. And then for my remaining columns, I've got just positives multiplying. So I'll get positive, positive. So I've now figured out exactly what's going on with both velocity functions. Let's now compare them. Okay. So I did this already, but I'll do it again. So I know I have t equals 0. At t equals 1, okay, something interesting is happening. I know that at t equals 1, the velocity of particle j changes from negative to positive. At t equals 2, something interesting is happening. Okay, the velocity of particle h changes from negative to positive. And then after that, I'll go all the way up to 5, because that is the end of my time interval. So let's think about what's happening here to my different velocities. So I have vh of t, and I have vj of t. Well, let's have a look. For vh of t, we are negative up to t equals 2, and then the velocity turns positive. For particle j, we're negative up until t equals 1, and then we turn positive. So where do these velocity functions have different sign? Well, they're both starting negative and turning positive, but Vj turns positive sooner. So I have this little region between t equals 1 and t equals 2, where down here, Vj is already positive, but Vh is still negative. So this tells us that the time interval that we're interested in is t being between 1 and 2. Okay. So how are the points divided up here? We have to do a little bit of work to explain our answer. Okay, we wanted to give some indication that we were looking at the sign of these velocities. So I get 1 point for considering the sign of one of the velocity functions. I then get another point for doing the same analysis for the other particle, the other velocity function. And then we're going to get a third point for our final answer. But we do need to do something like say, this is happening because I'm looking at this interval because I want to know where the signs are different. Okay, we need to have some sort of explanation piece there. So, good work. On to part C, we're now being asked about the speed of particle j. Not the velocity, but the speed. So at time t equals 2, we want to know, is the speed increasing, decreasing, or neither? Okay. So this is a classic question you're going to be asked in this kind of setup, asking, is the speed increasing, decreasing, or neither? So here, what you're really being asked to do is compare the signs of the velocity of particle j. Okay, because remember, velocity is just speed together with direction, together with sign, positive direction, negative direction. So we're comparing the velocity, the sign of that, whoops, and its derivative, okay, which we can also just think of as the acceleration of the velocity. Okay. By comparing these signs, we'll see if maybe we're traveling in this direction, but our acceleration is in this direction, the opposite direction. That, although we'd be traveling in this direction, we're decelerating. So our speed would actually be dropping. The other possibility is that we're traveling in that direction and we're accelerating in that direction. In that case, we're going to be getting faster and faster in that direction, so our speed would be increasing. That is why in a question like this, we're really just wanting to compare the signs of v, the velocity, and a, the acceleration. Well, this is actually really nice because we don't have to do too much work. We're told the acceleration, okay, v prime, at t equals 2 is positive, and we have an expression for the velocity. Okay, so we can pretty quickly figure out that at t equals 2, the velocity is 2 times 2 times 2 squared minus 1 all cubed. I could work out what this is, but I could just notice, hey, it's positive. Okay, because I've got that 2 squared minus 1, that is going to be 3. I'm cubing it, multiplying by 2, multiplying by 2. Going to be positive. We already figured out, actually, in part B, that the velocity was going to be positive in this region. So, however we get this, we know velocity at t equals 2 is positive. We were also told for free that the acceleration, which is just v prime, is positive. So because they both have the same sign, we're in the situation where velocity, we're traveling in the positive direction. Acceleration is increasing us in that direction too. So we're getting faster and faster and faster in the positive direction. So we're going to say, since Vj of 2 and V prime of 2 both positive, our speed is increasing. That's all there is to it. So how are the points given up here? Well, I say points, there's only actually 1 point. So we needed to get that final answer, but we also had to give some kind of reasoning, okay? Something to do with the signs both being the same, okay? If we just give unsupported work, we're unlikely to get the answer because we were told to give explanation. Let's move on to that final part. Okay, part D is again asking us about particle J. It's telling us where the particle started off at time t equals 0, and it wants us to figure out where the particle ends up at time t equals 2. This is just a net change theorem problem in disguise. Let me tell you what I mean. So we can break this journey up into 2 pieces. Right? We can have the initial position, and that is at t equals 0. And then I'm just going to add on the net change. Okay, how did I travel from getting from t equals 0 to t equals 2? Okay, we're told the initial position was x equals 7. So I've got 7 plus, how do I figure out a change when I have a rate? I just integrate, right? So this is going to be the integral of the rate, okay? So the rate of change of position for this particle is the velocity. I've got that rule there. So I want to integrate 2t t squared minus 1 cubed dt. What are the limits of my integral? Well, I'm starting at t equals 0 and I'm traveling until t equals 2. So if I can figure out this definite integral, that will give me my final answer. Great. How do we do this? Well, you might just be able to do this integral by inspection, okay? But if we don't spot exactly how to do it, hopefully we spot there's something substitution-y going on, right? Because I have this piece of the function, this factor t squared minus 1, it's being raised to the 3rd power, but the derivative of the derivative of t squared minus 1 is just 2t, which I see hanging out with a dt outside of that cubed power. So that's making me think probably can do a substitution. Let's see how that's going to go. So let's take our new variable to be that t squared minus 1. If I take the derivative of both sides, I get du equals 2t dt. That is great because my 2t dt is exactly what I saw upstairs in the dt integrand. So I'm going to be able to write this as 7 plus the integral of, well, it's just u cubed du when I do that substitution. Need to figure out the limits though, right? Okay, so I know that t was 0 up to 2. So in that case, u is just going to be t squared minus 1. So I get 2 squared minus 1 is 3. 0 squared minus 1 is minus 1. So I get minus 1 up to 3 as the new limits of the du integral. Well, I can do this integral, right? Definitely by inspection. So this is going to be 7 plus 1/4 u to the 4. Okay, undoing the power rule. And my limits are still -1 up to 3. I get 7 plus 1/4. Let's now do our substitute in our limits. So I'll get 3 to the 4 minus -1 to the 4. Okay. Now we can actually stop here, because remember, we're not being tested on our basic arithmetic. Okay. So we would stop here and get full credit if we wanted, but since I have you here, we'll just figure out this is actually 27 for us. Okay. So that's it. That is the final position of our particle using the net change theorem, using the integral of our rate of change of position, velocity. How were the points given out here? Well, I got 1 point for knowing to integrate the velocity. Okay, so if I write down something like that integrand, okay, I'm going to get that first point. I then, however I got there, knowing that this is the correct antiderivative to be working with, going to get as our second point, and our third point is going to be our correct answer. Whether we went all the way to 27 or not, that is how we're getting that final point. Nice job. Okay, how did you get on with this position velocity problem? As I said, this is classic AP calculus stuff. So if you're practicing this, you're going to be in great shape for these exams. Now, if you're working through this exam in order, you've now got one FRQ left, that's number 6. If you're working these in order, I'll put a link to the playlist for this exam here. If you want to try your hand at some multiple choice problems, I'll put a separate link to a different playlist right here. And apart from that, I will just say, looking forward to seeing you in the next video. Thanks for sticking with me. See you next time.